Hello and welcome to another session in physics. In this session we will be looking at the topic production of continuous electric current. But before that, let us review the previous lesson. Welcome back. At this point, I'd like us to talk about the production of continuous current from mechanical energy. Remember when I told you about how energy is neither created nor destroyed, but can only be transformed from one form to another. The same way too, it is possible to create electrical energy from mechanical energy. And that is when we talked about something like a motor, an electrical motor that is responsible for converting mechanical energy to electrical energy. Now, the process is really very simple. From the device you see here of a simple electric motor, rotor and stator, and we have a force that is applied at what we call a prime mover. This prime mover is what drives the armature, the rotor. The rotor is a thin device, not necessarily thin, but it is metallic in nature. It is metallic. The essence of it being metallic is so that it is able to conduct electricity. It is brought in contact with this stator here, made up of a magnet. Now, as this rotor or the armature is moving and rotating inside the magnetic field system, remember that this magnet is part of what we call a stator. So because of the presence of this magnet, a magnetic field has been created in this system. A magnetic field has been created. Now, a metallic conductor, which is the rotor, has been introduced into this magnetic field. Now, this rotor or armature, as it's called, continues to rotate in this magnetic field, and it ends up cutting across the magnetic flux or the magnetic lines of force that have been produced by the magnet. And remember that it is not natural for lines of force to cut across each other or intersect against each other. So as a result of this intersection, an EMF will be induced in the coil of the armature. This is based on Faraday's law of electromagnetic induction. So because of the presence of this magnetic field, an EMF is induced inside this system. This EMF can now finally be supplied to an external load, and we say that electric current can start to flow. Because it is an EMF that gives rise to the flow of electric current. Without EMF, there will be no current flowing. There will be no current flowing. Think of it as a car that has been parked. Let's say this is a car, for example. With its tires. Now, this car, there is no driver inside. And then you notice that this car is just moving. I mean, I'm not talking about driverless cars, because with the advent of 5G technology, we've had driverless cars now. But with the traditional cars that we know, imagine a car moving with no driver inside it. Would you feel comfortable being in such a car? Of course, without 5G technology, the answer is no. Because we believe that for a car to move, there either has to be a driver moving this car, driving it, or there has to be some sort of force, perhaps technology, causing this car to move. Or there could be people at the back of this car, pushing this car and causing it to move. That is the only way that this car can move. In the absence of any of these influences, this car will continue to remain at the same spot until it deteriorates. The same principle applies to currents. Electric currents are stagnant. They will not move. They will not cause electricity to happen unless there is a force that pushes them. When this force pushes them, it causes electricity to start moving. Now, what is this force that is responsible for pushing electrons? This force responsible for pushing electrons is what we call EMF. The full meaning of EMF is electromotive force. Electromotive force. That is the full meaning of EMF. It is the work done in moving a positive charge, a unit positive charge, from infinity to any point in a conductor. Now notice that at the end of this device there is something that looks like a meter. This meter is called a galvanometer, and this galvanometer is used to detect the presence of very small quantities of electric current. Remember that the speed of the rotor determines the magnitude of the induced EMF, because the faster the rotor moves, the faster and the more it cuts across the magnetic lines of flux, and these magnetic lines of force are what will determine the magnitude of the EMF that is being produced. So the more they are being intersected, the more the magnitude of the induced EMF. So this is a more holistic view of the diagram. You look at this loop, the coil or the loop, and then a magnet is being introduced. The closer this magnet comes to this coil or loop, this coil of copper wires, the more there will be a deflection on this galvanometer to show that when a magnet is brought in contact with a metallic conductor, EMF is induced there. Faraday discovered this, and he discovered that either you bring this loop closer to the magnet or you bring the magnet closer to the loop, either way, when one of them is moved away from each other, this meter reads, which shows induced EMF. Let us also look at how current is produced continuously from chemical energy. When we talk about production of continuous current from chemical energy, we're talking about cells. We're talking about cells, two dissimilar metals that are separated by a solution of various acids or salts. Now these metals are what we call electrodes, and the solutions, the salts, the acids that they are submerged in are called electrolytes. Electrodes are divided into two. We have the anode, which is the positive electrode, and we have the cathode, which is the negative electrode. In some situations too, there are times when this anode can have its polarity reversed and it could turn into the negative electrode, and then the cathode can become the positive electrode. It all depends on the kind of experiments going on and the kind of electrolyte that is being used, or the kind of production of continuous current being implemented at that point in time. So as you can see critically from this diagram, for now our negative electrode is our cathode and our positive electrode is our anode here. Here you notice hydrogen bubbles, and then you notice oxygen, and then you see that here the electrolyte is water here, H2O. That's what they are talking about here, and a voltage of 9.12 volts has been applied across the system to test for the presence of electric charges, to help to provide the EMF needed for electric currents to flow. What is a cell? Well, the diagram or the symbol for cell in the study of basic electricity is simply the symbol here that I drew. I'll draw it again. Capacitors look basically the same as that of cells. They just have the same kind of diagrammatical representation. A cell is a device that we use for converting chemical energy into electrical energy. A cell is a device that we use for converting chemical energy into electrical energy. So you think of things like your batteries. Batteries are made up of acidic substances that help to convert chemical energy into electrical energy. Now let's look at the production of continuous current from heat energy. Production of continuous current from heat energy. Before that, I'd like to take us back a little bit, and I'd like to point out that when it comes to cells, we have two basic kinds of cells. You learn that in subsequent classes. We have the secondary cells and the primary cells. Put simply, secondary cells are cells that can be recharged after they've been exhausted, and primary cells are cells that are made to be used once and for all. They cannot be charged. They can't be charged. So you just have that at the back of your mind. Now back to what we're trying to talk about, the production of continuous current from heat energy. This is done when the ends of two dissimilar metals are joined or inserted in cold and hot water, and then a galvanometer is connected across them to detect the flow of charges. Now what you see here is what we call a thermocouple. Now in this thermocouple we have what we call the hot junction and the cold junction. The two materials, the copper and the other material, they are intersecting at the hot junction, whereas at the cold junction they do not intersect. The reason for this is because the greater the difference in temperature between the hot and cold junction, the greater the current flow, and it also helps to establish a potential that makes it possible for there to be a deflection on the galvanometer to actually test for the presence of charges. And that's it for today. Thank you for joining us in this lesson, and to refresh your memory in what we've just discussed, please take the test that will appear on your screen.